Okay, welcome back to 11.6. We're going to talk now about some special types of geometric series. They're called infinite geometric series, which means they go on and on forever. Hence, if you look at these examples, they end in the dot, dot, dot. We're going to look at a couple of these partial sums of these infinite geometric series, and we're going to look at the differences between the two types of series. So if you look at the first one, it's 2 plus 1 plus 1/2 plus 1/4 plus the next one would be 1/8 and then 1/16 and so on and so forth. So when I ask for S sub 1, I'm asking for the sum of the first term, which basically just means the first term. So the first term is 2. Okay. When I ask for S sub 2, I'm asking for the sum of the first two terms. So it's 2 plus 1, which would equal 3. When we're asked for S sub 3, we're asked for the sum of the first three terms. So it's 2 plus 1 plus 1/2. Okay, oops, not 1/3, 1/2. Which equals 3 1/2. Okay, then when we're asked for the first, the S sub 4, we're asked for the sum. I don't know why that window keeps popping up. We're asked for the sum of the first four terms. So it's 2 plus 1 plus 1/2 plus 1/4. Okay, 1/2 and 1/4 is 3/4. So that's 3 3/4. Kind of an ugly 3. 3 3/4. Okay, and of course S sub 5 is 2 plus 1 plus 1/2 plus 1/4 plus 1/8. Okay, and if we were to add that up, it's basically taking 3 3/4 and adding 1/8. Okay, so 1/8 would be 2/4, so it would be 3 5/4. No, I'm sorry, 1/8 is not 2 1/4. So it would be 3 7/8. Okay, so take a look at these sums. These sums are actually approaching a number. We say they're approaching a number. I have 2, and then I have 3, and then all of a sudden I have 3 1/2, 3 3/4, 3 7/8. Okay, what do the numbers seem to be getting very close to? They actually seem to be getting close to 4. And in fact, they're never actually going to reach 4, but they're going to get awfully close, because the next, if I looked at the next sum, S sub 6, I would be adding a 16th to this, okay, which is not going to get me to 4. And the next time I'd be adding a 32nd, which is going to get me even closer to 4, but not to 4. So we say that these sums are approaching 4. Okay, now let's look at the next one. It's quite a different sequence or series. So S sub 1 is 1. S sub 2 is 1 plus 3, which is 4. S sub 3 is 1 plus 3 plus 9. 1 plus 3 plus 9, which is 13. Okay? And then the next one is 1 plus 3 plus 9 plus 27. I think you guys get the idea here. Plus 27, which would equal 40. And then the next one is 1 plus 3 plus 9 plus 27 plus 81 would equal 121. Okay, now let's look at these sums. They're quite different than the other ones. I have 1, whoops, didn't mean to cross that out. Okay, I have 1, 4, 13, 40, 121. Do you see how these sums are getting bigger and bigger? Okay, the next time I'd be adding 243. And the next time I'd be adding an even bigger number and an even bigger number and an even bigger number. So what these numbers are actually approaching is something that we already know about. It's called infinity. These numbers are approaching infinity. The difference between the sequences is, in the first one, each time I add a number, I'm adding a smaller number, and then a smaller number, and then a smaller number. So my sum is approaching something. It's approaching 4. In the second one, I'm adding a bigger number, and a bigger number, and a bigger number. So this second one is actually approaching infinity. Okay. So let's take a look at these two sequences. See if I can get all this on my screen here. The first sequence is said to be something called a convergent sequence. It's convergent because the sums are approaching a number. The second sequence is said to be divergent, and it doesn't have a sum because the sums seem to be approaching infinity. If you notice the two sequences, the first one had a common ratio of a half. The second one had a common ratio of a third. It's the fact that that first one has a common ratio of a half means the terms are shrinking. The one that has a common ratio of 3 means the terms are increasing. So the only one that has a sum is an infinite geometric series where the common ratio is somewhere between -1 and 1. Okay? If the common ratio is between -1 and 1, and that doesn't include -1 and 1, then the sum exists. If it doesn't have a common ratio between -1 and 1, the sum doesn't exist. If the sum does exist, it's a very simple formula. It's t sub 1 over 1 minus r. So let's take a look at some examples here. Okay, it says for each geometric sequence, each geometric series, find the sum. If the series has no sum, say so. So a couple of things we have to identify here. What's t sub 1? T sub 1 is 24. And what's our common ratio? What are we multiplying by every time? and we're multiplying by negative a half. Okay? Since that common ratio is between negative 1 and 1, this series has a sum. And that sum is, that's an S, again, not a 5, t sub 1 over 1 minus r. So t sub 1 is 24 over 1 minus negative 1/2. Okay? So that becomes 24. 1 minus negative 1/2 is the same as 1 plus 1/2. 24 over 3/2. And if we remember correctly, dividing by a number is the same as multiplying by its reciprocal. So that's 24 times 2 over 3. And that answer is 16. So that one definitely has a sum, and the sum is 16. Okay, let's take a look at number 2. T sub 1 is 8. Now the common ratio here may be a little bit hard to see, because you can't really think, oh, what do I multiply 8 by to get 12? If you want to know what you multiply 8 by to get 12, you actually do 12 divided by 8. Okay, you work a little backwards. 12 divided by 8 and reduce it is 3 over 2, which is 1.5. Okay, is that common ratio between 1 and negative 1? No, 3/2 is equivalent to 1.5. Okay, so it's not between 1 and negative 1. So therefore, this is one of those ones we say is divergent, and it has no sum. Okay, basically, if your series is, the terms of your series are increasing, then you're not, and it's an infinite, in other words, it goes on dot, dot, dot forever, and the terms are increasing, it's not going to have a sum. Okay, all right. Let's take a look at number 3 now. This is one of those ones I gave you number 3 because sometimes it's a little difficult to tell what R is. Okay, so first of all, let's identify T sub 1. T sub 1 is 500. And R, if you can't figure out multiplying forward, you actually divide backwards. So you do 400 divided by 500. So you do 400 over 500. So your common ratio is 4/5. Okay, is 4/5 between negative 1 and 1? Yes, it is between negative 1 and 1, so this has a sum. And the sum is equal to, and we don't have an S sub n here, we just have a sum because it's an infinite amount of terms. The sum is equal to T sub 1, which is 500, over 1 minus R. 1 minus 4/5. Okay? So that's 500 500, ooh, that's a big 0, over 1/5. Because we would change 1 to 5/5. 5/5 minus 4/5 is 1/5. And again, that would be 500. Instead of dividing by 1/5, you multiply the reciprocal times 5 over 1, which would equal 2,500. So these terms are approaching 2,500. They're never going to get to 2,500. They're going to get really, really close to 2,500, but they'll never actually get there because we're just going to keep adding a smaller number and a smaller number and a smaller number until we get to 2,500. Okay. Number 4. Number 4 is an infinite geometric sequence. Okay. So we first have to identify t sub 1. So t sub 1 is when we put 1 in for n. So it would be 2 to the first over 5 to the first. So that would be 2/5. And our common ratio, which we saw this in the last section, when you have this fraction in here, that's actually your common ratio. So your common ratio is 2/5. So t sub 1 is 2/5 and r is 2/5. Since 2/5 is between -1 and 1, this thing has a sum. And the sum is equal to 2/5 t sub 1 divided by 1 minus r. So that becomes 2/5 over 3/5. And then, of course, instead of dividing, we multiply by the reciprocal. So that becomes 2/5 times 5 over 3. Which is 2/3. So those sums are approaching 2/3. Okay. And lastly, one more problem. Write the first 3 terms of this sequence where t sub 1 is 40 and s is 200. Okay? In this case, we're looking for r. We don't have r. So we know our formula is s equals t sub 1 over 1 minus r. Okay? We know s. This time they told us s was 200. We know t sub 1. It's 40. And our unknown is r. So it's over 1 minus r. Okay? So we can take this equation and we can solve it for r. So I'm just going to put my 200 over 1, and I'm going to cross multiply. So that times that is 40 equals, and then that times that is 2. Wow, that's really big. Fix that. (200) parentheses 1 minus r. Okay, so you can go ahead and distribute your 200. So 40 equals 200 minus 200r. Subtract the 200 over to the other side to get negative 160 equals negative 200r. Dividing both sides by negative 200, I get r equals negative 160 over 200, which reduces to, over negative 200, because I have to divide both sides by negative 200, which, reducing, I can cross those zeros out, and it reduces to 4/5. So r is 4/5. Okay? So now we found r, but they want us to find the first three terms of the sequence. Well, we already know the first term. The first term is 40. Now remember, this is a geometric sequence. So the first term is 40. So to get the second term, I have to take 40 times my common ratio of 4/5. So I'll put a parenthesis, 4/5, which becomes, the 5 can cancel with the 40 to be 8, so I have 8 times 4, which is 32. And then to get the third term, I take the 32 times the 4/5. Okay, and I don't think anything cancels there. 5 doesn't go into 32 evenly. So we just go ahead and multiply the numerators. Pretend the 32 is over 1. Multiply the numerators and multiply the denominators. So 4 times 32 is 128 over 5. And that's it for your infinite geometric series.